want to talk with you today about one of the many reasons people do mathematics, to predict the future. And I want to give you an example of what I mean by that. Along the way, we're going to look at mathematics and some of its beauty, some of its power comes from it being so abstract, and also talk about why that makes it a little bit difficult. Now, most mathematics was developed to solve some problem that people had, some way of looking at the world. And the idea is that if you can develop some mathematics to understand the world, you can then figure out how the world is going to change, how things are interrelated mathematically, and you can use that to better understand the world and eventually to predict the future, to know what's going to happen. Today, I'm going to talk about mathematics and music. You see, when I'm not teaching mathematics at St. Mary's College of Maryland, I'm a violinist. And violins, like all the other string instruments, have a lot of mathematics in there. There's a lot of mathematics to study a vibrating string. There's also a lot of interesting math in vibrating tubes of air. If you're musically inclined, you should think about things like flutes, oboes, clarinets, bassoons, even all the brass instruments. They're all tubes of air. And in fact, I brought along with me today a tube of air so that we could study that. Here's a tube. It's just a PVC pipe, and it has a particular pitch. You can imagine if this tube were longer, it would play lower, and if it were shorter, it would play like a piccolo, much higher. Today, I want to ask the question, we get this pitch when it's open on both ends. What would happen if I close the other end and play it again? Do you think it would go up to a higher note? Do you think it would go down to a lower note? Or do you think it would stay the same? Well, I just told you that mathematics is supposed to predict the future, so let's see if we can do a little mathematics and predict the future and answer that question, and then we can check our work by actually playing it on this tube. Now, if we're going to understand this mathematically, we would do something like this. We would define a function u of x and t, which is the pressure inside this tube at position x and time t. And we would do things like look at how that pressure changes. There's a lot of algebra, there's a lot of calculus, there's a lot of differential equations involved in this. And it's fairly complicated math, but I want to try to get across to you today the key ideas in that mathematics. So mathematicians would define this function that describes the pressure, and then we would do things like understand the boundary conditions. Now the boundary condition when I have this open is that the pressure is atmospheric pressure. It's open to the outside atmosphere here and at the other end. Now inside, pressure could build up. There could be a lot of molecules close together, or we could have low pressure. It could be less than atmospheric pressure. Now one of the things mathematicians do to make this easier is we'll just define 0 to be atmospheric pressure, and then we might have positive pressure here, or lower pressure, lower negative pressure. But in order to predict the future, we're going to need to understand how air moves. Now, we know when you see a weather map and you see a high pressure system over the Midwest and a lower pressure system somewhere else, you know that the winds are going to move from the higher pressure to the lower pressure. And the same thing happens in this tube. If we have high pressure here and low pressure here, the air is going to move there, and that's what's going to create vibrations to give us our sound. This is fluid dynamics, and physics tells us exactly how that's going to move. And when we have those physical equations, then we can develop a differential equation which exactly models how the air is going to flow. It's going to be really important that in our differential equation model, we have these boundary conditions where the function goes to 0 on both ends. Now, I don't want to get into solving this equation today. That would be quite a long process. But I do want to show you the solution. We can solve this, and one of the things you should see is that there are a lot of familiar things in the solution. You can see trigonometric functions that you probably saw in high school. You can see pi, the irrational number. You can see the sigma, which is the sum. You might have seen that in calculus. So what this is telling us is it's the sum of a bunch of different functions. And we're going to look at those functions in more detail. You can learn a lot from the solution to the differential equation. You can learn things about the overtone series that's produced on a tube of air like this. You could learn exactly what pitch is going to be produced on a tube of this length. And that would allow you to actually make your own flute. You see, flutes have holes in there, and the holes are positioned sort of to create boundary conditions so that the tube is only going to vibrate up to that first hole. And if you knew the function which told you what pitch is going to be produced, if you wanted to create a particular scale, you could punch holes in particular places and make your own flute that played music that you liked. But if we look at this geometrically, if we look at the solution geometrically, it's telling us that we have to fit sine waves in here, which are 0 at both ends in order to match the boundary conditions. You remember the sine function starts at 0, goes up to 1, down to 0, -1, and then back up to 0. And we could squish or stretch that sine function. And what the solution is telling us is we have to squish and stretch that so that it's 0 on both ends. And that's really key. So we can solve that, and that's what happens when we have this open tube. We get that solution where it's 0 at both ends. Now, what if we change the math? If we change the math, what we're really doing is we're closing off this end, and the boundary conditions have changed now. And if we think through that, if we think through the mathematics, we're still going to be open to the outside air here, so it's still going to have to go to 0 here. At this end, the function is actually going to have to be maximal. It's going to have to be one of its peaks or one of its troughs in order to satisfy the differential equation. And we can look at that graphically. You see, the function for the open tube is going to have to go from 0 up and then be 0. That would be the longest wavelength we could fit in there. And that's what note this is. But if we close this end, the function is going to start at 0 and go up to its maximum at the closed end. Now, if we extend that function would hit its maximum and it would go back to 0 over there. And in fact, you could see that the wavelength of this is going to be about twice the length of this tube. And there's our prediction. We would predict that the wavelength produced from a closed-ended tube is going to be about twice that of the open-ended tube. Now, musically, if you look at these things, sounds that have double the wavelength are actually down about an octave. And now there is our specific mathematical prediction. We predict that if we play this tube open and then close it, the sound should go down about an octave. That's the prediction. Let's see how we did. There's the note. It's down about an octave from here. Here it is, it's closed again. Yay, math, we did that. Now, you might actually know something about this from just experience with musical instruments. You see, a flute is open at both ends. The flautist doesn't cover the mouthpiece entirely. That's open to the atmosphere. So a flute is open at both ends, whereas a clarinet is closed at the top end. The mouthpiece of a clarinet is entirely contained inside the clarinetist's mouth. There's no air escaping there. And that's why the fact that a flute and a clarinet are about the same length, but a clarinet plays about an octave lower. The lowest note a flute can produce is around 250 hertz. The lowest note a clarinet can produce is way down around 165 hertz, almost an octave lower. And this mathematics of an open tube versus a closed tube tells you that that's why a clarinet can play so low. Now, this is something that happens in math all the time. We just did all this math to understand air moving inside of a tube like this. But the same exact mathematics could model a vibrating string. So it's the same math that tells you how my violin's string vibrates when you pluck it. And in fact, this is fairly amazing. It's the exact same math that tells you how an electron moves around. Quantum mechanics, when you do quantum mechanics and you solve Schrödinger's equation, what you're doing is you're finding out that electrons can only have certain energy levels. And those energy levels, or it's the same mathematics that's telling you only certain sine waves can fit inside of this tube. This is something that comes again and again in mathematics. We develop mathematics to understand something in one field, and then it's applicable in all these other places. In fact, we're sort of used to that from grade school. You know, we learn how to do addition, and we learn how to add things like, I don't know, apples. But then that same addition, we can not only add apples, we can use that to add fish. We can add cinnamon rolls. We can add spark plugs. Addition is just addition. Addition is this abstract thing that allows us to add any objects. It doesn't matter what object you're talking about. And when we develop algebra that'll help us solve some problem in biology, that same exact algebra might help us understand something in economics or in archaeology. Henri Poincaré had this, he's a French mathematician, he had this great way of saying it. He said, mathematics is the art of giving the same name to different things. The same name to different things. That's the abstractness of mathematics. It allows you to describe all of these different phenomena with one common thing, the same mathematics. And math is powerful and beautiful, in part because it's so abstract. It allows us to be applied anywhere. But it also means that mathematics is difficult to learn. When we learn mathematics, we're learning it in the abstract, not usually in one area or another. We teach mathematics to students so that they can go out and apply it in whatever field they're interested in. And that's part of the struggle, is that we're teaching them in this abstract setting. But on the other hand, it's worth it to struggle for this mathematics, because mathematics is opening up these worlds. It's allowing you to understand the world around you. It's allowing you to predict the future. Thanks for watching, and I hope you stop by the MAA's website to learn more about the wonders of mathematics.